Welcome back, students. We are basically discussing stereochemical strategies, and today we will try to give you the final note on stereochemical strategies, and we will be basically discussing today a concept which we already explained you many times. The title of today's talk will be consequence of C2 symmetry in synthetic planning. Now, when you talk about symmetry based strategies, we have mainly focused on sigma v containing molecule, and we said that perfectly symmetrical molecule which does possess a sigma v, we can have a proper guideline for synthesizing those molecules, and strict maintenance of symmetry was always necessary. At that point, we also said that another symmetry element, C2 symmetry element, plays a very unique role in synthetic design, and throughout some of our experience or problem, when you said that if you have a C2 symmetry in your molecule, if it is constitutionally symmetrical, the left half and right half becomes homotopic, that is having an extra advantage. Now, before we try to go into detail, I will just again draw a very simple C2 symmetric molecule, which is basically a chiral molecule, is a chiral pool, is a tartaric acid. Now, tartaric acid, the way it has been written, you can just allow the rotation around this carbon, and then you can write this chiral tartaric acid in this way. Now, this is a very unique example of constitutionally symmetrical molecule, where left half and right half is similar because their sense of chirality is similar, and this molecule basically possesses a C2 symmetric. Now, if you try to just think in a different way, I will say that tartaric acid will write in this way, the hydrogens I have omitted, and then I am saying that the right hand side I will be writing this way. Now, the particular central bond we did not draw it. Now, see these two molecule, they do not have a plane of symmetry. Now it is quite clear if they have plane of symmetry, why I always said that if you have a sigma v, this left half and right half is enantiotopic. Now, see this tartaric acid, the left half and right half having same sense of chirality, because this OH is here above and this OH is below, but you are viewing it from the opposite side. So, they exactly have a same sense of chirality. So, for C2 symmetry, the point is same sense of chirality, is very important. So, in terms of C2 symmetry, you can always say that if you having a molecule, let us take the tartaric acid example. I am saying that tartaric acid is this, and I am saying that the left half and right half having exact same sense of chirality, and this bond are basically making in this way. Similarly, you can also devise molecule like this, where you can find that you put some extra methylene. This also has a perfect C2 symmetry. So, means that you have a methylene spacer. So, this methylene spacer joins the two homochiral halves. This halves, homochiral means they have a same sense of chirality, homochiral halves means two half which is having same sense of chirality have been fused through a achiral methylene bridge. Now, C2 symmetry plays a very important role in synthetic design, particularly we will be explaining with the help of tartaric acid example first, and in the nature many of the natural products are C2 symmetric, mainly due to the fact that sometimes two homochiral or same sense of chiral molecules basically dimerized. So, if they dimerize, one is say R configuration, one is say S configuration, sorry R configuration, both are having same configuration, dimerize through a achiral spacer and gives a C2 symmetric molecule. Means that if you have a only R isomer, if you can join through a achiral spacer, you can access those target molecule. So, you basically need a same sense of chirality to access C2 symmetric molecule, that was very important. Now, coming to the tartaric acid case, I say you are having this tartaric acid, this either D or L and is having a perfectly C2 symmetric. We will try to do some synthetic reaction. Initially I say okay. Now, the consequence of C2 symmetry is, as it is consistently symmetrical, the left half and right half are homotopic, means that this OH and this OH are homotopic, this CO2H, this CO2H are homotopic. Homotopic means they are basically exactly equivalent. So, now I say I will reflux this compound with acetone. So, means that this things will be now will giving you this compound acetonite protected. Now, I am saying that excess lithium aluminum hydride I will now put it here. So, both these carboxylic acid will be now converted to OH. Now, C2 remains here, C2 remains, the symmetry element remains. Now, by doing this, now I am saying that this CH2OH and this CH2OH are homotopic. So, what does it mean? Means that now I am giving you a simple one equivalent of TBS chloride, sodium hydride one equivalent, basically the McDougall's protocol which you have earlier explained. So, you expect that one CH2OH will be protected, it is fine. So, now we are trying to do the protection. So, first time I will put the protection on the left hand side, it gives you this compound, and then now on the other side I will do the protection here. Now, these compounds are basically same, these compounds are same, because if you take any of this compound, just rotate 180 degree and then in plane rotation they will give you the same compound. That is the beauty, of C2 symmetry, because they are fused with same homochiral halves, they are basically equivalent. Now, sometimes if this equivalence you cannot do by simple symmetry analysis, what I advise, you assign the RS configuration of these two center, you will find that RS for this and RS for this will be same, these compounds are basically same. Now, in C2 symmetry we or if you have a C2 symmetric target molecule, I am saying that now if you have a C2 symmetric target molecule, C2 symmetric target, basically we follow two different strategies. The strategy, first one is named as core expansion strategy, and second one is named as dimerization strategy. Now, both the strategies are basically similar in sense. In case of core expansion, I will be just explaining what is core expansion strategies. So, we are basically discussing if we are having a C2 symmetric target molecule. Core expansion strategy, we say there is a strategy which named as core expansion strategies. Now, what I will do? I will give you a target molecule. I am saying I am giving you a target molecule. The target molecule structure is one, two, 3, 3,4 dihydroxy cyclopentanone. Now, see the stereochemistry, this molecule having a nice C2 symmetry. Okay. So, now I am saying that okay, your starting material has to be tartaric acid, okay, has to be tartaric acid. Now, actually this problem in reality we have analyzed earlier when we talked about the synthetic equivalence, but still it is a very unique strategies. Now, I am saying that this starting material also having a C2 symmetry. Now, see this OH and this OH belongs to this OH and this OH, only thing is you need to expand this OA. So, basically this core needs to be expanded, this core. So, this is the core, I am saying this particular core needs to be expanded. So, core need to be expanded, that is why it is called core expansion strategy. Then reality how it was done, if you having a tartaric acid, as I said, first you convert the carboxylic acid to diester by a ethanol H plus treatment, number A. Number B, just protect with this acetonite, then what we will get? We will basically get this acetonite protected CO2 ET, CO2 ET. You do a lithium aluminum hydride reduction and then do a Apple reaction. Now, these reactions basically we have already studied, so we are not discussing in it detail. So, what will basically get? You get this CH2I, CH2I. Now, in core expansion strategies, the left half and right half are reacted in a same way. I mean, you basically expand through both way, and then I am saying that you try to react with a D1 ampolong, 2D1 ampolong. Now, 2D1 ampolong you can basically easily generated from a formaldehyde dithion. So, then this basically after this alkylation your synthesis will be almost completed. So, only thing is you need to remove the dithion group by Hg2 plus first, and then you remove this acetonide protection by a acidic treatment, you get your target molecule. So, this is in principle the core expansion strategies, and C2 symmetry remains intact, C2 symmetry remains intact. We will next show that how, or we will next analyze how this dimerization strategy is in. This dimerization strategy was basically a similar like core expansion strategy, but as I say dimerization means that maybe your target molecule is such that you need to dimerize the two homochiral halves. So, your compound will be something like this, you have a one homochiral half and you have a another homochiral half. Homochiral half means they have a same sense of chirality. If they are enantiomeric to nature, they will be heterochiral. Now, here I am saying this homochiral half and two homochiral halves you basically dimerize through some achiral spacer. So, now next I am giving you a target molecule, then see how you can analyze it. I am saying your target molecule is okay. I am saying that this is a target molecule. Now, if we analyze very closely, it is basically a C4 tartaric acid building block on the left hand side. This left hand side having a one chirality and this right hand side have exactly the same chirality. So, that is why both the halves are homochiral, and then you are dimerizing it through a achiral spacer. So, eventually these things you can easily prepare if you just try to have a compound like this. So, basically trying to simplify the structure in terms of C2 symmetry, and now I am saying that if you have this compound and this achiral spacer, you can simply do a SN2 type of ether formation to this to compute the target molecule. Now, this left half and this right half are basically same. These are same compound or homochiral halves. Now, eventually this compound you can easily make as discussed earlier. So, how you can make this compound? This compound you can easily make if you having this free alcohol by simple Apple reaction OPG by Apple transformation. Apple is very known to you, and this one definitely you can easily prepare from the C2 symmetric diol just by monoprotection OH. So, this you can prepare from tartaric acid. Now, this part your C2 symmetry there. So, as C2 symmetry is there, you can basically do the monoprotection, and no matter where your protection group goes, it will basically give you same compound. So, this halves and another same halves. So, the two homochiral halves are basically dimerized through achiral spacer, and that gives you a target. Now, in nature you will find many C2 symmetric compound do exist. I will try to give you some example just for your structural viewpoint. So, the idea will be quite clear. This is one of the C2 symmetric compound. There are few methylene bridges in between, not bridges, basically CH2 CH2. There are 12 methylene in between 1, 2, 3, 4, 5, 6, 7, 8. So, this compound is basically a kind of a dimer where two homochiral halves are joined. Now, this compound is a natural product, is a gamma lactone based natural product. Its name is ansepsinolite. If you see its structure, ansepsinolites, probably you can say that these methylene groups are the achiral spacer, and in reality. So, I will just analyze the structural viewpoint, and eventually this molecule does have a perfect C2 axis of symmetry. So, now if I try to say that if you have this compound and if you have this compound, what you basically need to do? You basically connect here and connect here. Now, this compound and this compound are basically similar, because in plane rotation of this compound, in plane I am now saying in plane rotation, that is basically give you the same compound which was written in the right hand side. So, these two homochiral halves, this half and this half is basically dimerized through this achiral spacer. That is pretty important, and that gives you the ancestral light. So, in nature there are similar kind of compounds do exist, and sometimes if you find this kind of C2C symmetry compounds are there in your structure, your synthetic experiences or synthetic strategies will always tell you that to start with a same sense of chirality. Now, we will try to do the ancestral retro. We first draw the retro. We probably won't discuss it in detail. We will just try to give you a idea how this ancestral can be done in reality through a dimerization strategy. So, this basically falls to a dimerization strategies, and here there will be CH2 actually. So, CH2 you can just put CH2 11. So, CH2 11 1 CH2 12. So, this basically the achiral spacer. Now, what I say? I am saying that if you have some compound something like this, now you need to put some reaction or some group where you can find that. So, I am saying X CH2 12, and then you are having this another homochiral halves of the same lactone. Put it X prime X prime. Now, I am saying if you have these two compounds, their sense of chirality is similar. Now, this X we are not putting any stereocenters, because finally, if you see the double bond has to be created here, double bond has to be created. Now, if I say that this X prime and X prime are good leaving group like bromo or bromo, and this X is a electron withdrawing group like sulfone SO2pH, then the strategy will be quite similar or quite simple. Now, I am saying that if X is SO2pH, you can easily generate a carbanion here, it is adjacent to the carbonyl and adjacent to the SO2pH. Same thing can happen here, you can easily generate a carbanion here. Now, these two carbanion basically having a same sense of chirality will now react with these two bromo in the left hand side as well as right hand side. So, this is basically the dimerization. We put the achiral spacer and left hand and right hand, we are trying to fuse it with two homochiral halves. So, if you do these things, next see what kind of compound. So, you just treat with a base. Now, how this chiral halves we are accessing, probably we are not discussing it here. So, I am writing SO2pH, and then you will be basically having SO2pH. So, in between there are 12 methylene. Now, things are absolutely simple. You basically need to do a elimination of this hydrogen, elimination of this hydrogen. So, yesterday we talked about a selenoxide elimination, similarly sulfoxide elimination also quite possible, and now if you can simply heat this compound, your 1,2 sulfoxide scene elimination will takes place. So, elimination will takes place, and that will basically give you the target molecule. So, what exactly we do? It is basically a dimerization strategy we have used The dimerization strategies, we have said that it is you basically take two homochiral halves and dimerize through the achiral spacer. This is a very nice demonstration of dimerization strategy if your target is having C2 symmetry. So, that is very important. It was very important to memorize all those things. A couple of molecules, probably I can draw it here, which might have. Now, this particular example is very important. This N pyrrolidine compound, this compound, it looks this compound is a natural product. Its name is pyrrolidine 197B. Now, with its structure, if both the groups are same, then the molecule has been perfectly C2 symmetric, but as both the groups are not perfectly same, this molecule now belongs to a pseudo C2. Now, pseudo C2 are also similar like C2, like we call pseudo symmetry. Similarly, you have a pseudo C2 symmetry element in this molecule. Now, for this kind of pseudo C2 also, you can exactly apply the similar kind of strategy what you do for the C2 symmetric strategy, because C2 symmetry, the advantage is you can start with a homochiral or same sense of chiral precursor. Now, here you need to create two particular stereo center. Now, probably I will give you as a thought process. You go and you start thinking on your own that how this compound can be created, but let us try to give you a hint that how this compound you can create it. And if you see the structure, this compound basically having two methylene in between, So, I will put this 2 methylene in between, and then I will try to draw the base epoxide. Now, this epoxide basically is a 6 carbon epoxide. If you remember, this epoxide we have synthesized in the chiral pool strategies from D-mannitol. Now, as this epoxide is C2 symmetric, you can basically functionally manipulate this epoxide to basically by using some suitable nitrogen nucleophile if possible. Now, this compound is C2 symmetric means that if you use one equivalent of nucleophile, probably it can, no matter if it attacks here or if it attacks here, it will give the same compound. So, initial for pseudo C2 molecule is always advisable to start with a perfect C2 symmetry and then take the help of the homotopicity. Now, here basically depending on this C5H11, C4H9, you can open the epoxide. So, C5H11 means only one CH2 is there. So, now you can think about opening with 1 carbon extra nucleophile, then you have this OH here, same thing you do it here also, you get OH, and then this OH you basically need to convert to corresponding amine. So, you can convert this OH to some mesylate, then you can replace it with ammonia to get access of this target molecule. So, this should not be a problem for you. Similarly, I will try to write another molecule which is also a C2 symmetric natural product, and this is compound having a 8-member structure, and this 8-member structure is having this particular on the left hand side, and then with this nitrogen you have this achiral spacer. So, 1, 2, 3, this 3 I think it's 4, yeah, this is a this 4 carbon, then you are having this so the left hand this same compound now was this compound. Now, if you this compound is a natural product, its compound name is homalene. This also again a C2 symmetric compound, C2 symmetric compound. This is C2 symmetric compound. If you see it, you do this target analysis, you will find that if you have this particular compound as your starting material, and then you can basically couple with 1, 2, 3, 4. You can just couple with X and X, it is a 4 carbon, X stands for bromide, and then this right hand side you write the same compound in a opposite way. Now, this opposite way means these compounds are basically same sense of chirality. So, this strategical exploration through C2 symmetry was very useful. Now, this left half and this right half are basically homochiral, or they have a same sense of chirality, So, now you can basically make it, and do not worry if you cannot make this compound, if you cannot make this compound is fine, but your visualization should basically guide you. If you have two same set of chirality, you can just join them through a chiral spacer to give you a perfectly C2 symmetric molecule. So, C2 symmetry in that way is very useful, and nature always prefers normally in nature you will find more C2 symmetric compound than sigma V containing compound, because nature always prefers homochirality. In case of sigma V, if the molecule does belong a sigma V, means that two heterochiral halves has to be fused, because we have a mirror plane of symmetry which bisects into two enantiomers. So, that is a heterochiral half. So, in that way C2 symmetry is very useful, it is very informative, and say probably we will stop the stereochemical strategies here. We will try to explore a few things, because we have probably few lectures left, and so have a good time. Till then, goodbye.